All right, page 2. All right, there's the third case. So the first two cases, first case where you have two real roots, second case where you have a repeated real root, and then the third case is where we actually get complex roots. So we have complex numbers for our solutions, and we don't want complex numbers. We want real solutions for our differential equations. So this is how we're going to work through that. A y double prime plus b y prime plus cy is equal to 0. So again, here we have a second order differential equations where we have constant coefficients. A, b, and c are constants. We go ahead and substitute in, so we have am squared plus bm plus c equals 0. And now after we substitute, we're going to find that using the quadratic equation to find our zeros, we get negative b plus or minus the square root of b squared minus 4ac all over 2a, where our determinant, b squared minus 4ac, is going to be less than 0. And now, because this is less than 0, we have a negative underneath the radical, and this is where our complex numbers are going to come in. So, our solution will be, we're going to use alpha to represent our real solution for the negative b over 2a, plus or minus I, because we have imaginary numbers, times beta, which is going to represent the determinant over 2a, with the I, the negative underneath the radical, pulled out. And so then our solution is going to pretty much match our m sub 1 is going to equal e to the alpha plus I times beta, and our m sub 2 is equal to e to the alpha minus the imaginary times beta. And plugging back into our general solution, y equals c sub 1 e these should not be e. This our m sub 1 is just alpha plus imaginary times beta. M sub 2 equals alpha minus imaginary times beta. So we have y equals c sub 1 e times our m sub 1, which is going to be alpha plus the imaginary times beta times x, and plus c sub 2 e to the m sub 2, which is alpha minus the imaginary times beta times x. And now, we don't really want to put our solution this way because there's a better way to write the solution. So I don't know if you remember Euler's formula. Back from Calc 2, where we have e to the ix, and that's equal to cosine of x plus the imaginary times sine of x. And the way that you were able to find the solution to this was doing it in a Maclaurin series for their e to the ix. And this is what we're able to reduce to. Now, we don't have everything in terms of this, but if I look up here and I see, hey, here's my c sub 1. It's e to the alpha plus alpha plus I times beta x. I can use this solution right here. So if I take this first solution and I look at it as e to the alpha plus I beta x. I'm just going to rewrite it real fast. And then I go ahead and try to simplify this. I'm going to go and distribute my x. So I'm going to have e to the alpha x plus the imaginary times beta x. And then with addition and an exponent, it's really just e to the alpha x times e to the imaginary beta x. And now what I can do is I can now substitute in right here e to the I beta x into Euler's formula. Instead of having e to the ix, I can have e to the I beta x, and that's just going to equal cosine beta x plus I sine beta x. And I can do the same thing with the second equation, or the second solution. So e to the alpha minus I times beta, all that times x. I'm going to rewrite that here. And I'll just go ahead and substitute in. So we have e to the negative I beta x, and that's going to be equal to cosine negative beta x plus I sine of negative beta x. Well, from pre-calculus, we know that cosine of negative beta x is going to be an even function, and sine negative b of x is an odd function. So then we can rewrite e to the negative I beta x is equal to cosine beta x minus I sine of beta x. Now, adding these two equations together and then subtracting the two equations together, we get our solution for our differential equation with constant coefficients when we have complex roots. And that is, here's our general solution. Y is equal to e to the alpha x times c sub 1 cosine beta x plus c sub 2 sine beta x. And so this is what's going to be our solution when we have complex roots with a differential equation with constant coefficients.